Good afternoon, Year 9. Let's get the right PowerPoint up here. Here we go. Here's a starter. Have a go at these questions here. You should know all of these by now. So pause it, and I'm unpausing and moving on. So all of those. If you don't, learn them. Very important. Okay. Now, as I mentioned before, we can't be doing practical at the moment, but we can be looking at some of the practical associated skills, which are in the assessment objective 3, which is there on the screen there, which is about looking at data, getting stuff from it, drawing conclusions, and so on. Okay, and thinking about experimental procedures. So this is what we're going to look at today, and it's all to do with specific heat capacity. Okay, so let's move on. Just refresh your brains. This is what you've done in your previous lessons. You know that specific heat capacity tells you the amount of energy needed to make 1 kilogram of a substance get hotter by 1 degree, and it's specific to the substance. So water, 1 kilogram of water takes that amount to get hotter by 1 degree. Copper takes this amount here. Okay, fairly simple stuff. And this is a property of the material. That's our definition. If you're ever asked that in any situation, that's a 2-mark answer, because specific heat capacity is the amount of energy required to raise it 1 kilogram by 1 degree. Okay, if you just say it's the amount of energy needed to make it get hotter by 1 degree, that's 1 mark. It's specifically 1 kilogram by 1 degree. Okay, and there's the formula that you've used before. And just a note here, that delta sign there stands for change. So you've had to go applying that formula, and in this lesson you're going to be finding the specific heat capacity, but not using the formula, but by graphically. So let's have a look at this experiment here. Okay, student is given 2 unknown metals. The 2 blocks of metal, one's labelled X, one labelled Y, and their task is to identify which metal is which. Okay, we've got some information here about specific heat capacities, and we've got that from a textbook because that's a specific value for a particular metal. And so they do this experiment. So let's look at the experiment. Here's our metal block, and inside the metal block we've got a heater, an immersion heater, which is connected to a joule meter, which is connected to the power. So when I switch this on, energy will flow. This will record the amount of energy flowing, and obviously that energy will get transferred to heat energy in the heater and then to the block, and then the block will get hotter. Okay, is that fairly standard? That's fairly simple. If not, go back to the previous lesson and have a think. Okay, but so the students done the experiment. They've done that experiment. They've carried it all out. There's a bigger picture of it. They've recorded the energy. They know that the mass of the block is 1 kilogram. And here we go. They've recorded the temperature to a resolution of 1 degree. That means that their scale on here is to only 1 degree. That's what we mean by resolution. If they used a digital thermometer, their resolution might be 0.1 degree. Or if they had a really expensive thermometer, it might be 0.01 of a degree. So the resolution is telling us about the smallest degree of change we can measure here. Okay. So this is the data they will collect. They'll do the experiment once with metal X, and every 30 seconds they will measure the temperature of the block, and they will also record the energy that's been supplied. So they do that experiment once for X and once for Y, and they get this set of data here. Move this just out of the way. Whoops. Let's move that out of the way. Good. So looks like a big frightening table. So they've done the experiment for 10 minutes, and then every 30 seconds they've recorded the temperature. Now what you need to do is to plot a graph of energy and temperature, with energy on the y-axis and the temperature across the x-axis. Okay. Notice these scales are number lines. So for your temperature, I would choose a scale that perhaps went from 20 as being the lowest number, all the way up to at least 36. I'd go up to say 40 and go from 20, 22, 24, 26, 28, 30, or somehow to get that to fit on to your graph paper and using a lot of space. Okay. The energy will go up the side, and you've obviously got to go up in 250s by the look of it, all the way up to 5,000. So draw those scales in, make sure the number lines are correct, and then you are going to draw a best fit straight line. Plot your points. Now, if you are neat and you've got big enough graph paper, you can get both of these plots onto one bit of graph paper. Otherwise, just use two. Okay. Now, to give you an idea of what you're being marked against, these are the success criteria here, graphing and analyzing. So for the graphing, look at this set of criteria. If you can tick all of these boxes, that's a perfect graph. I will leave that for you to look at that. You've drawn graphs before. There's the data there. So you can pause this and then move on, okay? So unpausing. Once we have our graph plotted, and here's a sort of, whoops, let's move this out of the way again. That's where it's there. So I've plotted my points and notice that when the energy was 0 input, this is my first starting temperature. I think that was 22. So I've plotted my points and then I've added a best fit straight line and drawn that like that, okay, with a ruler. I can now find the gradient. The gradient is what's going to tell me in this case what the specific heat is. To find a gradient, if you've not done this in maths, listen in now because it's very simple. We draw a triangle. Along that line somewhere, we pick a point on the line there, pick a line there, we draw a big triangle, as big as we can get it, at least taking half of the length of that line. And then we look at the energy change here. Look, I've called that delta E, the change in energy. So how much energy? So in other words, the energy at this point, take away the energy here. It tells me the difference in energy there. And then the difference in temperature across the bottom. And I've called that delta T, change in temperature there. Okay, my gradient is equal to that delta E divided by delta T. I do the sums, and that gives me a value of the specific heat in joules per kilogram degree C. Have a think, have a go at doing that, okay? And then moving on, finally, find both your gradients. Now, these are the questions then that you can answer, and this is going to be teacher marked. And these are sort of evaluation questions and questions asking and sort of testing your understanding and your ability and so on. Now, these are marked against this marking criteria here. Let's have a look at that. Let's see if I've got a bigger version. There it is. This is how we write scientifically. This is a level 3. If you're a level 3, you are writing good science. Okay, your writing is well structured, no grammatical errors, and there's detail and it's coherent. Level 1 is just facts or process are being identified simply. What we're looking for you to be at is somewhere up to level 2, between 1 and 2 at your age, at your stage. You may have some level 3 writers. So have a look at those and bear those in mind when you answer these. Okay. So I'm going to pause those. And that's about it. This, this PowerPoint is on Teams. If you can print out the data, that's great. Hopefully you'll be doing it in class, in which case your teacher will be sort of chivvying you along, because this is quite a lot to do within one lesson. So you've got to be on the ball. Okay. And what we're looking for in these writing scientifically answers is some good examples of your English skills. Okay. Right, apologies for my sore throat again. I will see you soon.